Welcome back. This is part C of concepts of 7, 8. We are going to do one more example. Evaluate integral negative infinity to infinity 1 over 1 plus x squared dx. Notice here the lower limit is negative infinity and upper limit is positive infinity. So from what we have defined earlier, whenever you have negative infinity to positive infinity, then we can actually choose a value between negative infinity and positive infinity. We can split the integral as sum of two integrals, one negative infinity to a, the other one a through infinity. So that is exactly what we are going to do in this problem. We're going to choose the value between negative infinity and infinity as 0 in this case. So we are going to split the integral into two parts. So we are going to write the integral I, which is equal to negative infinity through positive infinity, 1 over 1 plus x squared dx, which is going to be written as sum of two integrals. One is negative infinity to 0, 1 over 1 plus x squared dx, plus integral 0 through infinity, 1 over 1 plus x squared dx. We will evaluate them separately. We'll each integral separately. So we'll first evaluate so we'll call this as step number 1. So we will evaluate, we will call this one as say I1 and this one as I2. So let's evaluate because this is 0 through infinity. I1 is what I'm going to be evaluating first. The integral 0 through infinity 1 over 1 plus x squared dx. It is again improper integral of type 1 because it's over the infinite interval. So this is equal to limit as t approaching positive infinity, integral 0 through t. So anytime you see either lower limit or upper limit in terms of infinity, you have to change that to t, then allow t to approach infinity or negative infinity, whatever the case may be. In this case, positive infinity. So we are allowing t to approach positive infinity. So 1 over 1 plus x squared dx, which is limit t approaching infinity. Integral of 1 over 1 plus x squared is inverse tan x between the limits 0 and t. So limit as t approaching infinity. So it is tan inverse of t minus inverse tan 0 and limit as t approaches infinity. Inverse tan 0 is 0, so it is actually tan inverse or inverse tan infinity that is equal to pi halves. Tan pi by 2 equal to infinity, right? So that's why inverse tan pi by 2 equal to infinity. So inverse tan infinity will be equal to pi by 2. Let's compute I2, which is negative infinity to 0, 1 over 1 plus x squared dx. Here the lower limit is negative infinity. So limit as t approaching negative infinity, integral t through 0, 1 over 1 plus x squared dx. This will be tan inverse tan of x between t through 0 and t is approaching negative infinity. So it is t approaches negative infinity and it is tan inverse 0 minus tan inverse t. Inverse tan of 0 is 0, then we have negative of tan inverse of negative infinity which is equal to negative of negative pi by 2, which is equal to pi by 2. The value of I2. The value of I1 was pi by 2. The value of I1 is pi by 2. The value of I2 also turns out to be pi by 2. Now going back to step 1 and plugging in the values of I2 and I1, we get I, substituting I1 and I2 into step 1 or I, we get I equal to, we got I2 plus I1, which is equal to pi by 2 plus pi by 2, which is equal to pi, which is a finite limit. So now if you notice the tan in 1 over 1 plus x squared graph looks like this, and you are determining the area from negative infinity through positive infinity. Even though the area looks as if it's infinite area, it is not. Here the value of the limit happens to be, the value of the integral turns out to be pi, so the area under this graph is finite. Hope this video helps. Example 4, for what values of p is the integral 1 through infinity 1 over x power x to the power p dx convergent? Integral 1 through infinity 1 over x to the p is convergent whenever p is more than 1 and divergent whenever p is less than or equal to 1. It is convergent whenever p is more than 1 and it is divergent whenever p is less than or equal to 1. You already saw one example in the beginning of this section that integral 1 over x square 1 through infinity turned out to be equal to 1, and we mentioned that this integral is convergent. So you notice here the p-value here is equal to 2. So this will happen for any p-value more than 1. So the integral 1 through infinity 1 over x to the p is convergent whenever p is more than 1 and it's divergent whenever p is less than or equal to 1. We know that integral 1 over x dx in 1 through infinity turned out to be infinity, which is divergent, and this one is convergent. So here p equal to 1, right? The p value is equal to 1. So we are not going to get into the proof of this, but we will be applying this not only in this section, but later on in chapter 11, when we do series convergence and divergence and testing of convergence and divergence, we will be using this idea a lot. So keep in mind that integral 1 over x to the p, where integral 1 through infinity, is convergent whenever p is more than 1 and diverges when p is less than or equal to 1. Watch my next part of the video, which is the next part of the video for the for type 2 integral, improper integrals and examples.